Okay, so let initial horizontal velocity be ux. Okay, that's in the horizontal component of our initial velocity. Okay, be ux. Ux is 0.4 meter per second. Let initial vertical velocity be uy, and its uy is equal to 0 because we are told it's projected horizontally. So there's no vertical component. It's not projected at an angle. Okay, so it's completely horizontally. So all of that is going to ux 0.4. The horizontal distance sx, horizontal distance moved by the ball, can be obtained using s equals uxt. Remember from second equation of motion, Newton s equals ut plus half gt squared. Our a is now g, acceleration to gravity, and it's 0 because there's no horizontal effect for acceleration, right? Okay, so basically what I'm trying to say is that the horizontal distance, this is our horizontal distance, okay, from foot of the tall building or foot of the cliff to where the ball lands on level ground. Okay, so that horizontal distance, I can call it sx. Okay, remember s from this, so this is our s, but it's horizontal. Okay, and our a has become g because our acceleration is due to gravity, and it's 0 because gravity does not have effect, doesn't have effect in the horizontal for horizontal motion. So all of this initial velocity is the same initial velocity at this point. So throughout the journey, ux does not change. Okay, but time of flight, so time of flight is not given, so we could have just slot it in and find our horizontal distance. So we need to find time. So I must mention that the connection between a horizontal motion and the vertical motion, the horizontal motion of the object or projectile and its vertical motion, the only connection, the only common quantity that connects them is the time of flight. Because the time it takes to go from here down to land down here is the same time it takes to just drop, if it was to drop. So if it was free fall, just like this free fall, okay, it is just time, the same time it takes to drop from top of the cliff to the bottom here, the same time it takes to travel horizontally. Okay, so it's only time of flight. So let's get that time of flight, which is a common denominator. So the vertical distance moved by the ball is obtained using sy. I'm using sy as in the vertical distance. So slot that into this equation. Okay, I am specifying the direction. I'm specifying the components I'm dealing with. So vertical height, this is what I mean by vertical height. So it's given by, of course, we are going to use the vertical component of our initial velocity uy times t. Remember Newton's second equation of motion for uniformly accelerated motion. So uyt plus half gt squared equals to gt half gt squared because uy is 0. There is no, it's horizontal initial velocity. See, uy is 0. There's no vertical component for that initial velocity. So uy is 0, take note. So all of this is 0. So we're left with half gt squared. Our g, we can take it to be 10. And we're given that the height, remember the question says a height of 20 meters. So the vertical height, which is sy, slot it in here, 20. So if you cut, see that t becomes 2 seconds. Okay, so we've gotten the time of flight. The time, which is common to the horizontal motion. The time is what's common to the horizontal motion of our projectile and the vertical motion of our projectile. So we've gotten the time, so we can use that to get the horizontal distance, because the question says calculate the horizontal distance moved by the ball. So let's slot it into the same second equation of motion. Okay, so having calculated time of flight, the horizontal distance sx now, okay, is all distance but in distance in horizontal direction moved by the ball can be obtained sx equals to uxt, because of course the half gt squared is gone because there's no gravity, 0 for the horizontal direction. So slot that in 0.4 times 2 because 0.4 is our initial, so that gives us 0.8. So an object is projected horizontally from the top of a cliff with a velocity of 7 meters per second and lands on the ground level at a point 56 meters from the base of the cliff. Calculate the height of the cliff. Acceleration due to gravity g is equals to 10 meters per second squared. So the object is projected horizontally from the top of the cliff. Okay, so this is what it looks like: cliff, the top of the cliff, and then the base. So it's projected horizontally. So it's straight horizontally with this initial velocity of 7 meters per second. So there's no, okay, so this is entirely u in the horizontal component, in the horizontal direction. All right, so it's noteworthy that only the time of flight t is common to the height and horizontal distance covered by the projectile. Only the time of flight is common to the height. This is the height, vertical distance covered, and this is the horizontal distance covered by the projectile. Okay, so only that time of flight connects them. So first, to obtain the time you slot it to the second equation of motion. There's no acceleration for horizontal distance, so it's gone. You only have uxt. 7 is our initial velocity times time. Okay, just to recap on this point, it's noteworthy that only the time of flight. The time of flight is basically the time of the duration of the journey of the object. Okay, so we are saying that the vertical distance is assume that, imagine that the ball or object was just dropped from this point. You just drop down. This is the vertical distance the object travels. Or if it just rolled from here to this point. So this is the horizontal distance covered, and this is the vertical distance. The only thing that connects both of them is that it takes the same time for both distances to be covered. Both horizontal distance and vertical distance take the same time. So if we can apply that time to this value, either of the value given. In this case, we are given the horizontal distance. So we have that horizontal distance equals to 7 times t, because this initial horizontal velocity times time. So our time is 8 seconds. So it takes 8 seconds to move horizontally. So we can apply it to the vertical height. Remember, free fall, because there's no initial vertical velocity. So uy is 0. So the graph will have gt squared. Slot that in and you have 320 meters. Alright guys, what we've done so far is looking at objects projected horizontally from a height. Projected this way. Okay, now how about a second case for objects projected at an angle theta to the horizontal? So look at this diagram. Objects projected at an angle theta to the horizontal. So imagine this is the point of projection. So it's projected with this initial velocity u. So you see it's at an angle to the horizontal. The angle between this u and horizontal, the x-axis, is theta. So and this object is projected at an angle theta to the horizontal. Okay, this is typical of footballs kicked over a distance. Typical of maybe bomb projectile, cannonballs. Okay, so we should study it. Basically, it will mean that we'll have. So let's look at what we have. Notice that one, at the instant of projection, that's point A. Instant of projection, the initial velocity u can be resolved into its vertical component and its horizontal component. Yes. Okay, so this initial velocity u can be split. See, remember we talked about resolution of vectors. So this u can be split into its vertical component u sine theta and its horizontal component u cos theta. Okay, so that's basically projectile motion. It's motion that goes in 2 dimensions. Okay, so it can be split. So the second thing we should notice that the horizontal component of the velocity u cos theta remains constant throughout the time of flight, throughout the journey from point A to E. Look at this u cos theta, which is the horizontal component, remains constant from start to finish, from point A to point E. Why? Because it's not under the effect of gravity. It's only this u sine theta, which is the vertical component, that lifts the ball or projectile off the floor. Anything that lifts the ball off the ground would definitely be affected by acceleration due to gravity. So that takes us to point 3. The vertical component of velocity u sine theta changes throughout the time of flight as it is under the influence of gravity g. So u sine theta, which is the vertical component of our u, changes because gravity will always affect it, either slowing it down or accelerating it. Okay, so that's what we are saying. Okay, so we've dealt with that the horizontal component of velocity, this u cos theta, is the horizontal component of our initial starting velocity, which is the velocity of projection, or the velocity with which the object is thrown. Okay, it's thrown, pushed, pushed with the initial velocity. So the horizontal part of that initial velocity just imagine just rolling on the floor, going horizontally. So it's not going to be affected by acceleration, that downward pull of acceleration of gravity. Now let's go to the fourth point, at point C. Point C is up here, that top there. At point C, the vertical component Vy has become 0. Okay, so you see there's only a horizontal component. The vertical becomes 0 because it slows down from initial u sine theta to 0. It becomes 0 at this point. So Vy becomes 0. So we have Vy here, like that. It becomes 0. Why? Because gravity is slowing it down. So at this point, C, which is basically the maximum height of your object, the maximum height that is scaled by the projectile or object. So at point C, the vertical component Vy has become 0. At this point, the highest point of our journey, is entirely horizontal velocity. The vertical component of our velocity has become 0 because of the slowing down or the deceleration due to gravity. So what can we say about maximum height? We can use the this is the third equation, Newton's third equation for uniformly accelerated motion, v squared, remember that? So this is our final velocity v, initial velocity, and acceleration we'll use acceleration to gravity for a, and this is going to be our vertical height or maximum height. So with that in mind, so remember, so at maximum height, point C, final velocity is 0. Remember I said it's slowing down to 0. There's a momentary stop of 0, so for final velocity is 0, so v is 0. U, we are dealing with the vertical component. So initially, remember, vertical component is u sine theta. The initial component, vertical component of our initial velocity, u sine theta squared, putting the square because there's square in the formula. Our a is now g, minus 2g here. This is our vertical distance, okay? All right? Okay, so that's how it goes. So the third equation of motion, we're trying to find the vertical distance, s. We know that final velocity has maximum height. We're trying to find the maximum height. So that's why our s is now h, maximum height. We want to get the maximum height. Knowing that at this point, our vertical component of velocity is 0 compared to its initial value of u sine theta, okay? So vertically u squared because it's a square there in the formula. All right, so minus 2g is minus because gravity is negative, it's pulling it down, and gravity in the negative direction. So plus becomes minus to show that it's decelerating the object. So make that the sum of the formula, make h divide both sides by 2g, and you have the equation, an expression for the maximum height of the projectile motion. Okay, the maximum height. So we have an expression of h is equals to u squared sine squared theta all over 2g. All right. So v, okay, so that is that s has been replaced by h, a has been replaced by minus g, and then my final velocity at point C as maximum height is 0. Okay. What else do we notice from our diagram? The time taken to attain this maximum height, h. The time taken to attain the maximum height. Okay, we can use the first equation of motion. Use the first equation of motion. We know that at maximum height, the vertical components for velocity is 0, Vy is 0. Remember, these are from first equation of motion, v equals to u plus at. Our acceleration is minus g because it's acting downwards. So a is now replaced by minus g. Uy is the initial vertical component of our velocities, and that's u sine theta, t is t. So we're trying to find the time taken to attain maximum height. We are using this expression, okay, where Vy is at maximum height is equals to 0, okay, not maximum height, okay, Vy is 0, and of course a is minus g. All right, so slot that in, make gt to the formula, I get u sine theta. Okay, now divide both sides by g, so t is equals to u sine theta over g. So hence, Okay, so this is the time of flight to get to maximum height. Now to get to maximum height and back down to ground level must be twice of this. So 2 times this is this, okay? So to buttress the last point, calculating time of flight. So we just calculated time of flight to go from this point of projection up to this place. So the time to to go for the object to get from this point of projection to this maximum height is t. Then to go from this maximum height down to the original level is another t. So t plus t is 2t. So we calculated t to be u sine theta over g, twice of t. That's because the total time of flight, okay, from point A to E, the whole movement from point A to C is t. From point C to E is another t, so t plus t is 2t. So 2 times of this expression will give you the total time of flight, which is 2u sine theta over g. Yes, still on it. Okay, next up, we need to find the horizontal distance. Another something what we need to notice about our projectile motion is the horizontal distance covered by the projectile. The horizontal distance is represented by r, okay? And it is not under, we observe it's not under any acceleration or deceleration from gravity. So this also horizontal distance covered by projectile represented by the symbol r, okay, or range. It's actually called range. R stands for range. So this is the horizontal distance covered by the projectile. So we can find an expression for this. You see, it's basically it doesn't lift up the floor, so it's not affected by gravity. So initial u cos theta at this point is the same u cos theta that will be at point E. So at point A, starting point, is the same u cos theta that will be at this end point. So we just simply have that. You can use s equals to ut, remember the second equation of motion, where a equals to, that is the acceleration. This a is 0 for s for horizontal distance. So our horizontal distance range, all of this becomes 0. You just ut, we're left with ut, okay? Alright, so to get the horizontal distance covered by the projectile r, which is the range, we slot it into this second equation of motion. This half et squared evaluates to 0 because there's no acceleration to the gravity for horizontal motion. So in the object doesn't lift off the floor. So gravity there's no acceleration due to gravity for it. So r becomes, we're left with just ut. And our u is u cos theta. That's the horizontal component of the initial velocity times t. The time here is you are going to use the whole time of total time of flight, because I'm dealing with the total time of flight. The time it takes to go from here to here is the total time of flight. The same time it takes to get from A to C and from C to E. So the total time to go this way is the same time it takes to just go horizontally. So we're going to use that total time of flight expression we derived before this and slot it into t, this t here. So we have 2u sine theta, remember t is equal to u sine theta. So u cos theta, everything u times u becomes u squared, we have 2. So this expression I put in brackets is this. Okay, so still on our horizontal distance represented by r, range. So still on that horizontal, that's maximum horizontal distance range. We're saying that this expression 2 sine theta cos theta can be shortened into sine 2 theta by use of remember your trigonometric identities. So 2 sine theta cos theta can just be shortened as sine 2 theta. Okay, so look at that, 2 sine theta cos theta, bring down 5. So this in bracket is simply u squared sine 2 theta all over g. So this is the shortened form of our maximum horizontal distance, called range. So R stands for range. So we've got an expression for the maximum height h, the total time of flight t, and the maximum horizontal distance range. Okay, yes, let's take a look at that. That was the first one we did. Maximum height h. Okay, got an expression for height, got an expression for range, and the total time of flight. So we need to take note of these expressions, memorize them. Okay, h, total time of flight, and range. Okay, all right. Okay, so guys, a quick way to remember how to derive our expressions for projectile motion. Just look at total time of flight, R for maximum horizontal distance range, and H for maximum height. The equations of motion, we used Newton's 3 equations for uniformly accelerated motion. You just apply it in the reverse order. Remember this TRH. TRH is reverse order for alphabets. No, H comes before R and R comes before T. So just reverse it, TRH. Okay, so T, use the first equation of motion. Start deriving your expressions starting with total time of flight. So, and apply the first equation of motion, that's V equals to U plus AT. And then for R, use the second equation of motion, that's S equals to UT plus half AT squared. And finally for H, the maximum height, use the third equation of motion, V squared is equals to U squared plus 2AS. Okay, so that is a mnemonic we can use to remember how to derive our expressions for projectile motion. T, remember T is for total time of flight. Use the first equation of motion. R is for range, maximum horizontal distance. Use the second equation of motion. And H is the maximum height. Use the third equation of motion. Okay, and of course, remember where to use your vertical component, horizontal component, and acceleration due to gravity should be G. Look at a quick example on a missile. A missile is projected with a velocity of 250 meters per second at an angle of theta to the vertical. If the total time of flight of the missile is 25 seconds, the value of theta is what? A missile is projected with a velocity of 250 meters per second at an angle of theta to the vertical. If the total time of flight of the missile is 25 seconds, the value of theta is what? Okay, so this diagram gives us a picture of the question in example 3 here. So the missile is projected with a velocity of this 250 meters per second at an angle of theta to the vertical. At an angle of theta to the vertical. If the total time of flight, so total time of flight is given, so we can revert to our formula. Total time of flight, capital letter T is equals to 2U sine theta 1 over G. I'm using theta 1 to differentiate it from the theta in the question. Remember, this expression is for when theta is with respect to the horizontal. Our diagrams, our original derivations, all the equations we derived for theta is with this diagram. Theta is, right, so basically I'm using theta 1 to differentiate from the theta in the question. Okay, because theta 1 is given respect to the horizontal axis. Okay, if you look at the original diagram we used for our expressions, so theta is the angle with respect to the horizontal. Okay, but the question we are handling here, this question is with the theta is given with respect to the vertical. So I'm differentiating this theta from this one. I'm using theta 1, theta 1, theta 1. So you slap that into, okay, put that into the expression for total time of flight. You have theta, so you get theta 1 as 30 degrees. So basically just subtract theta 1, which is down here, from 90 degrees to give you the theta for this particular question. That's the angle of projection with respect to the vertical. So since theta 1 is with respect to the horizontal, then theta from the question, angle of projection, is equal to 9 degrees minus theta 1, which is 9 degrees minus 30 degrees. Okay, so theta is 60. So in short, this angle theta is with respect to the vertical for this particular question is 60 degrees. Okay, all right, so our expression, all our expression for total time, maximum height, range is theta with respect to the horizontal. Take note.